Okay, this next section is on individual gas laws. And this is looking at the relationships between temperature and pressure and volume and the amount of gases that we have. This is basically how we discovered the ways that gases work and why they work this way. Okay, so we've got 4 gas laws that you guys need to know. You don't need to know the names of the laws, although I'll give you guys the names of the laws, but you do need to be able to explain why this law makes sense with respect to the kinetic molecular theory. Okay, so let's try the first one. The first one is known as Boyle's law. This was English chemist Robert Boyle. Again, I'll never test you on that because I'm more interested in your knowing the chemistry than the history, but we call it Boyle's law. And he is looking at the relationship between the volume that a gas takes up and the pressure that that gas exerts. And he discovered that if I'm at constant temperature, and this is important, this is at constant temperature, so you're in the lab on the same day, you're not changing the temperature. He found that pressure and volume are inversely related. Or in other words, the pressure is directly related to the inverse of the volume. That's how we express mathematically the statement that pressure and volume are inversely related. This little thing here means proportional or direct relationship. It's not an equal sign, so it's not that this is equal to that, but we're going to say that generally it's proportional to that. Or we can we could make it an equal sign if we put in some sort of constant. Pressure is some constant, and we're not going to say anything about what that constant is, but some constant times 1 over the volume. And if we solve for the constant, we find that the pressure times the volume is constant. So the pressure times the volume then will never change. So what happens if the pressure goes up? What would happen to the volume in order to make sure that this remains constant? The volume would have to go down, right? The pressure goes up, the volume would have to go down in order for the pressure times the volume to remain the same. If they both went up, then this would increase, and that would not be the same as staying the same. And vice versa, if my pressure dropped, my volume would do what? The volume would go up. Exactly. All right, so we find that the pressure and volume directly related, and it's always constant. And this is interesting because it's always constant. I can take the same sample of gas and measure the pressure and volume and then make a change and measure the pressure and volume again. And we'll find that the initial pressure times the initial volume will be the same as the final pressure times the final volume, because they both are equal to the same constant, K. Does that make sense? Because my initial pressure times my initial volume equals K. My final volume pressure times my final volume equals K. Since it's always constant, then they're going to equal each other, okay? And now we can use this to do some interesting math. So let's say, for instance, we've got the pressure in a cylinder, 600 milliliter cylinder, or 600 milliliter container at a pressure of 65 millimeters of mercury. And if we increase the pressure to 385 millimeters of mercury, then what would the new volume be? I've got an equation right here. We've got some stuff to plug into the equation. So at this point, and I'm sorry for those of you who are really enjoying dimensional analysis, but most of chapter 8 is going to be algebra. So we're going to plug in these values and we're going to solve for the one that we don't have. Some of you are going to appreciate that. Robin is very excited about doing algebra instead of dimensional analysis. That's a little far off, Caleb. Let's see. Do I have anybody else? It's okay. Try it again. Robin got 101.3. I think that's about what I get. Anybody else getting that too? Excellent. Brooks got that answer too. That is 600 milliliters. Yeah. Sorry if that's not clear. 600. There we go. Okay, so if we plug this in, so then this is a unit of volume, right? So this is V1, and this is my initial pressure, my initial volume. This is my final pressure, and I'm looking for my final volume. Note here, we can leave this in milliliters if our answer is in milliliters. We can leave these in millimeters of mercury if my units are the same, and you'll see this when I do plug it in. So P1 was 65 milliliters of mercury. V1 was 600 milliliters. P2 was 385 millimeters of mercury. And then we're looking for V2. And now we solve for V2. What do we do to solve for V2? Exactly, perfect. Here, I'll do this in another. So red is our initial setup, and blue is what we're going to do to get that V2 all by itself. Divide both sides by 385 millimeters of mercury. So those cancel. Now, even though we're doing algebra instead of dimensional analysis, we should still keep our dimensions with us, because that'll tell us, hey, look, we are eliminating those units. We'll be left with those units, so we know what the units for our final answer will be in, which will be milliliters. So 65 times 600 divided by 385 should get about 101 milliliters for V2. You guys with me there? 101. Excellent. Okay, now here's the question, the test question. Why does this relationship between pressure and volume make sense according to kinetic molecular theory? Based on what kinetic molecular theory tells us that pressure and volume are. If we go back here, volume is total space occupied, pressure is force exerted on an area. What's going to happen when I take a sample of gas and I make it take up less space? Yeah, so the law says smaller volume equals higher pressure. But why? So I've got a sample of gas in a space, got some particles making collisions. I take that same sample of gas and I make it occupy a smaller space. I get an increase in pressure because, exactly, because pressure is collisions. But I take up less space, I have a smaller surface area, and since I have the same number of particles running around, they're going to collide with those walls more often. And collisions means pressure, so the pressure on the inside of that container is going to be higher. Does that make sense? You guys with me? Excellent. Okay. Next we have Gay-Lussac's law. Here we go. And a French chemist, Joseph-Louis Gay-Lussac, was studying the relationship between pressure and temperature. Let's see, where's my stylus? Here we go. And he was doing this at a constant volume. So I'm not changing the volume. He has these containers that don't change volume. And he's just looking at the pressure that's exerted as being related to the temperature. And he found that for a gas at constant volume, pressure and temperature are directly related. The way to say that mathematically is that the pressure is directly related to or directly proportional to the temperature. So if my pressure goes up, then my temperature would go up. My pressure goes down, then my temperature would go down. because they have a direct relationship. Before we continue, can you guys tell me why it is that pressure and temperature would be directly related? What does that make sense? They are. They're in lecture 8.1. In fact, I copied these. Oh, I'm sorry. No, these are lecture 8.1. These are in lecture 8.2. Okay, so Robin says temperature is a measure of kinetic energy. So the more heat you have, or the higher the temperature, the more movement you get. Okay. And Caleb's exactly right. Pressure is collision. So if you have more movement, then that's going to be a stronger, harder collision, more often colliding. If you have less movement or lower temperature, then you're going to collide with less force. You're going to collide less frequently because you're not moving as fast. So because pressure is collisions and temperature tells you how fast you're moving, you can get an idea you're going to be bouncing off the walls a lot more. That's going to be higher pressure. Okay, so we're going to play the same game we did with Boyle's law. And that is to say, this is just proportional, but if I put some sort of constant in here, this is a different k, but just constant k times t, then I can make that equal. And then we find, if we solve for k, the pressure divided by the temperature will be constant. So my initial pressure divided by my initial temperature is constant. My final temperature pressure divided by my final temperature is going to equal the same constant. And therefore, P1 over T1 equals P2 over T2, because that relationship is always constant. And then we can do math with these just like we did with the others. And this is the moment where I have to remind you, we have to use Kelvin. We must always use Kelvin, because Kelvin can never be negative and it can never be zero. So tell me, why would it be important, looking at this, equation here, why is it important that temperature is never zero? Yeah, J. Houston Joyce, you can't divide by zero. If you divide by zero, you get an undefined operand. If you try to do that on your calculator will freak out and not give you the answers that you want. So, and if you try to divide by a negative number, then you might get a negative pressure, and that doesn't make sense. It's not like you'd have negative force exerted on an area. So we're always going to need to use Kelvin for our temperature. Okay, so let's set up an example that you guys are probably familiar with. You've got a basketball. So this is a fixed volume basketball, and somebody left on the court overnight. And so in the evening, when we are like, say, 15 degrees Celsius, we find that the pressure inside that basketball is 400 millimeters of mercury. And then we find that the next day when we come home from school, that it's really warm outside. Let's say it's 100 degrees Celsius. No, wait. No, that's terrible. 100 degrees Celsius is not a warm day. 100 degrees Celsius is boiling water. You would die. Okay, so ignore my lecture notes for the moment, because obviously I think I meant 15 degrees Fahrenheit and 100 degrees Fahrenheit. And those are totally different than 15 degrees Celsius and 100 degrees Celsius. Look, even I can make a bad mistake like that. But you come back, the end of the day, nice warm day, we want to know what the pressure is on the inside of that basketball. Because you guys know, have you guys ever had that experience? Like, end of a warm day, it's like somebody came by and blew it up. It's got pressure inside it again. This is also, by the way, why when you take the air pressure in your tires, it makes a difference whether they're hot. Yeah, or cold. Exactly, Katie. That's exactly right. If you've been driving on that tire, then it's much warmer, and so you're going to get a different reading than if you do it when it's cold. Excellent. Okay. But help me out here. What's the first thing we're going to do to set this up? Yes, Brooks. Yes, 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 yes. The first thing is to convert this to Kelvin. So 15 degrees Celsius, 30 degrees Celsius. What do these become in Kelvin? In case you don't remember, Kelvin is Celsius plus 273.15. So my Kelvin values here should be, and again, I'll give you this equation on the exam. Perfect, 288 and 303. I'll drop that 0.15 because technically not significant. Excellent, okay. And now we're just gonna do algebra, right? What are we solving for? Let's see, we've got, this becomes your initial pressure, initial temperature, final temperature, final pressure. So that's what you're solving for. Excellent. Okay. I need at least 2 people to give me the same answer, and then I'll be sure that we're doing it right. For 20.8. That sounds reasonable to me. Anybody else get the same answer? Yeah, for 20.8. Okay, so here's one kind of trick to help if you're having a hard time with the algebra. Here I'm sorry. On this last problem, I set it up and then I did the crossing out. But it might be easier to solve for what you're looking for and then plug in your numbers. It feels a little bit cleaner and easier. So if you say, okay, I'm looking for P2, let me solve for P2 in this equation. So I'm going to multiply both sides by T2. And then I know I've got the formula for P2, that P2 is equal to P1 over T1 times T2. And now I can plug it in. So that's going to be 400 millimeters of mercury divided by T1, which is now 288 K, multiplied by T2, which is 303 K. Again, those units cancel out. Those are the units I'll be left with. 400 times 303 divided by 288, then 420 millimeters of mercury. Okay. So my pressure went up as my temperature went up. And that makes sense because higher temperature means more collisions. Excellent. Okay, any questions on Gay-Lussac's law? Let's see. Next, if there's no questions, then we're just going to move right on to Charles's law. So Gay-Lussac also referenced some work that he credits to a French chemist named Jacques Charles. And Jacques Charles was looking at the relationship between volume and temperature when you're at a constant pressure. So this is at a constant pressure. And he finds that volume is directly proportional to temperature. As the volume goes up, the temperature goes up. Or we could say as the temperature goes up, the volume goes up. Temperature goes down, volume goes down. And we could play the same kind of mathematical games we did there, making it equal sign if we put a constant. We find that the volume over the temperature will always remain constant. And we could say then that the initial volume divided by the initial temperature will equal the final volume divided by the final temperature, because they both equal the same constant. Before we do math with this, tell me really quickly, why would it make sense that if I increase the temperature, that I'll increase the volume? You're on the right track. Exactly, Robin. Increased temperature creates more collisions, and that would increase the pressure. But if you're at a constant pressure, then that increase in pressure actually will expand the surface so that to maintain that constant pressure, you end up taking up a larger volume. Does that make sense? Yes, perfect. Perfect, Brooks. This is exactly right. So our good example here, we had constant volume was a basketball because the basketball couldn't expand. It couldn't get any bigger. Therefore, as you increase the temperature, then your pressure increased. If we put an example here of a balloon, you blow up a balloon to a certain amount. If you increase the temperature, because the surface of that balloon is flexible, instead of just increasing the pressure, it'll actually expand that balloon to increase the volume. Okay, and this is what you're going to get in an air balloon, hot air balloon, but it's also what you're going to get, you know, if you just say blow up a balloon at room temperature and stick it in the freezer, and you come back and look at it in a couple of hours, then that lower temperature means that that balloon's going to take up less volume. You take it out and put it on the counter, and you can just watch it blow up again as the temperature rises. Okay, so that's in a place where we have a flexible volume, but constant, say, external pressure. Okay, so here's an example, and again, we have to always use Kelvin as our temperature. Always, always. So as an example, let's say hot air balloon has an initial volume of 955 liters at 56 degrees Celsius. And so then the next question is, what temperature is the balloon if my volume decreases to 875 liters? What would be my new temperature? I hope a couple of you guys are working on this. You're so quiet. I never know whether you're just waiting for somebody else to answer the question or whether you're doing it yourself. Okay, Katie and Robin, looks like you got the same answer. What are the units there? Is that Celsius, or I think that's Kelvin? Is that Kelvin? Okay, good. You all got the same answer, so I feel pretty good about that. 302 Kelvin, and you can convert that to Celsius if you wanted. Again, if we assign liters as unit of volume, so that's your initial volume, that's your initial temperature, this is your final volume. What you're looking for is your final temperature. If we take this equation and solve for T2, we're going to multiply both sides by T2, and then multiply by T1 and divide by V1. So when I solve this for T2, we should get that T2 is V2 times T1 over V1, and then we can start plugging things in. Again, easier to solve when you're just dealing with these little guys rather than all the numbers. So 155 liters times, we convert that to Kelvin, 56 Celsius is, what is that in Kelvin? .329 Kelvin. Perfect. Divided by V1, and our liters cancel, so we get our units of Kelvin. We know we did it right. And we plug all that in, and we should get 302 Kelvin. And if you wanted, you could convert that back to Celsius. We would find, let's see, 302 minus 273, it's about 29 degrees Celsius. Again, you don't need to do that unless, for instance, that's what I'm asking for. 3 Celsius. Okay, so as our temperature goes down, volume goes down. Everybody with me on Charles's law? Excellent. Okay, I've only got one more law to worry about here, and that is Avogadro's law. And this isn't was not discovered by Avogadro. We just named it after him because we thought that he was pretty cool and he deserved law in addition to his number because he's pretty sweet. Okay. And what was discovered here is that if you're at a constant pressure and you're at a constant temperature, your volume is directly proportional to the number of moles. Volume directly proportional. We use this little n for a number of moles. Now this should be really like obvious to you guys, right? The more gas I have, the more space it takes up. Does that make sense? You guys are like, why do I need a law for that? Why do you need a law for that? Hopefully you guys are like, oh yes, if I have more gas, it's going to take up more space. If I have more particles, they're going to take up more space. You guys with me here? I want you to see how obvious it is first, and then I'll tell you what's cool or interesting about it. So that's kind of the obvious thing. It's that, 1 liter of a gas has twice as many gas particles as a half of a liter. And 2 liters would have twice as many particles as 1 liter if you're at the constant temperature and pressure. Okay, but here's what's really interesting is that this is true of all gases and the same proportionality applies, which means that number of moles, that say like 1 mole of helium gas takes up the same space as 1 mole of, say, sulfur hexafluoride gas. Same volume, because the number of moles is the same, so the volume is directly proportional. And you might look at that and be like, oh, whoa, 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 slow down. This makes sense that the more moles I have, the more volume it takes up. But these are 2 different things. Helium weighs 4 grams per mole. Okay, so here's a little helium. Ba-dink-a-dink. Okay. Sulfur hexafluoride weighs 146 grams per mole. So let's say, that's what, 25, 30, 35 times bigger in terms of mass, if you think size is directly proportional to weight. So 35 times bigger. So here's sulfur hexafluoride as a molecule compared to helium. Why would they take up the same volume? A sample of helium gas takes up the same volume as the same sample of sulfur hexafluoride gas if you have the same amount. Why would that make sense? That makes no sense. What the? These are bigger. You guys tell me. This is in reference to the kinetic molecular theory here. So look at this. Tell me, which of these would help explain why? Exactly right, Robin. It's number 2. Number 2 of the kinetic molecular theory tells us the amount of space occupied by the gas particles themselves is so much smaller than the amount of empty space that we don't even care how big that gas particle is. So here we go. Yeah, it's true that this is bigger, but the amount of space taken up by a gas has more to do with the empty space between the particles than it has to do with the particle size themselves. And so just to give you an example, 1 milliliter of water, when we turn it from a liquid to a gas, becomes 1 liter of water gas, approximately. 1,000 times more empty space than there is space taken up by particles. So I don't care that this is 30 times bigger because I've got 1,000 times more empty space between them. So the size of the particle is pretty much meaningless when it comes to the space that a gas takes up. Does that make sense to you guys? You have this same sample container. Same sample container. I could only fit 1 particle in that sample container because mostly it's empty air. You guys with me? Robin's with me. Yay! Okay, Katie's 2 people with me. Excellent. All right. So here's what we take away from Avogadro's law. Here's the interesting thing that we take away is that we're going to say that at standard temperature and pressure, STP. This is like 1 atmosphere of pressure and 25 degrees Celsius. So like room temperature. We'll find that 1 mole of any gas is going to occupy the same amount of space, which in this case is 22.4 liters. So it's the same for any gas. So that's kind of interesting. All gases take up the same volume, so 1 mole, any gas at standard temperature pressure, 22.4 liters. Okay. Those are your 4 gas laws. Again, I'm not going to test you on what they're called, but you do need to know these relationships. This takes us back to our 8.2 in class activity sheet, and you're going to look at section 4. And I've got 4 questions that each refer to one of the gas laws, and you tell me which gas law it is and then solve it. These are questions exactly like the ones that we just did in our example. So if I give you initial pressure and initial temperature, and I'm asking for a final temperature, and I give you a final pressure, which is our law that relates pressure and temperature? That's Gay-Lussac's law. Good. And what is Gay-Lussac's law? Perfect. Yes. Your initial pressure divided by your initial temperature goes for your final pressure divided by your final temperature. Good. And remember to convert that to Kelvin. Okay, what about this one? We've got initial pressure, initial volume, give you the final volume, ask for the final pressure. Which law are you going to be using here? Boyle's law. Perfect. Then what's Boyle's law? Perfect. P1 V1 equals P2 V2. Excellent. Okay, what about this one? What is the mass of CH4 in a sample occupies a volume of 16.5 liters at STP? Which law are you going to use for this one? Avogadro's law. Perfect. What does Avogadro's law tell us? Yeah, it tells you your volume is directly related to the number of moles. And specifically, it'll tell you that 1 mole of any gas is 22.5 liters if I'm at STP, which I am. Okay, so if I've got a volume of 16.5 liters, could I use this to tell me how many moles the gas there are in that sample? Sorry, this was dimensional analysis. Threw a dimensional analysis problem at you in the middle of algebra. But you can do that. 16.5 liters of CH4. But we know that 1 mole of anything, including CH4, is going to occupy 22.5 liters of CH4. Does that make sense? You guys following me there? So this was the equivalency that Avogadro's law gave us. So we're just going to plug it in. Now, that doesn't get us our answer because we wanted mass, and I gave you moles. Uh-oh. Do you know how to find mass from moles? Which mass? Is this rude? I'm bringing in stuff from chapter 6, making you apply it all over again. Molar mass, that's exactly right. The molar mass is the mass that's in 1 mole. What's the molar mass of CH4? How do you find that? Perfect, Kelly got it. Take the mass of carbon, the mass of 4 hydrogens, and you add it all up. So about 16.04 grams in a mole. You can't forget how to do this stuff, you guys, because we're going to keep using it for the rest of the semester. If it wasn't the case, I wouldn't have taught it to you. Anyway, so that's how to do this one. Okay, next one, if I give you initial volume, initial temperature, and final temperature, Could you find the vital volume? What law is that going to be? Charles's law. Okay, and what's Charles's law? What's the setup for those? V1 over T1 equals V2 over T2. Excellent. Perfect. Okay, that's it for individual gas laws.